Welcome everybody. This is our fifth session in JEE mains previous year questions for chapter Alternating Current of class 12th. Before this video, we have made one video in this series and four videos in this series, and all of those videos are available on our channel's playlist section. I have also started similar series for NEET previous years. So if some of your friends are preparing for that, then you can watch those videos also or can guide them through those videos. And if you find these videos helpful, useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount will be highly appreciated. With this, let's start today's video. In the previous one, we completed around question number 30 or something. This is question number 28. Okay, and we have to start with question number 29 today. So let's slide it down. A series LR circuit is connected to a voltage source with V is equal to V node sine omega t. After a very large time, current IT behaves as. So for a LR circuit, we know that charging equation is given by this I node 1 minus E minus T by tau. This is a charging equation. And if we refer to the discharging equation, then discharging equation is given by this I node e raised to power minus T by tau. And as per the statement, there is a voltage source is connected to it. So means we will use the charging one. And in case of charging of we can say inductor, if sufficient time is provided to it, then its charging looks something like this. If I try to plot a graph here, sorry. So charging of an inductor looks something like this. That charging will occur and then it will saturate to the maximum value that is possible. Now we don't find any time of graph here, but this graph is starting from 0. Here this is time. Suppose on the x-axis, on the y-axis we have current. So this graph starts with value uh, of time from 0 and current also from the 0. But if we see all the available options, we can in the all the options we see that the graph is starting at t is equal to t node. In all the graphs, we are starting with t is equal to t node, and it is mentioned that t node is very large as compared to the uh, we can say time constant of this LR circuit. Now, if sufficiently large time is given to a LR circuit, we can put this value here and then we can analyze it. That if we give it a very large value, then this will become I is equal to I node 1 minus, suppose it is very large value. So suppose let's take infinity, negative infinity by tau. So it e raised to power minus infinity is 1 by e raised to power infinity, or it is almost 0. So I is approximately equal to I node. Means at that time value of current will be equal to the maximum current. Now if we use this, then we might think, sorry, that option A is the right answer, that I is equal to I node at very large time, or t is equal, time greater than t is equal to t node. But we have to also look into the voltage, as voltage is variable here. The voltage is following the sine curve here. Means if I draw it, if suppose this is our voltage, now I have drawn two cycles of voltage here. So this is the positive part of the voltage, or we can say this is the part where charging will happen. Actually charging will happen till here, After that, potential drops and there will be no further charging across the inductor. And then inductors keep on stay charged, and after this point discharging happens. So even after time t is greater than L by R, the value of current will not stay constant, because due to variation in voltage, charging and discharging will keep on happening. And in case of LR circuit, as already mentioned here, that T node is very greater than LR, we know that current lags behind the voltage. In case of an inductor and resistance circuit, current lags behind the voltage, and that lagging behind the phi is given by XL by R. And if it lags behind the voltage, then we can say value of current I, or formula for current, will be Vt divided by the impedance of the circuit. Now suppose impedance is Z, so it will be V node sine omega t minus phi, where phi is the angle by which current is lagging behind. And we can write it like I node sine omega t minus phi. Now in case of a circuit where I can say if XL is very large as compared to R, then this phi becomes almost 90 degree, and in that scenario I becomes I node sine omega t minus pi by 2. And with respect to that, then we can write it like minus I node sine pi by 2 minus omega t, and that will be minus I node cos omega t. Means our current will follow the graph of cos but with the negative sign. And if we see here, we have a graph of cosine that is there, but it does not have the negative sign. But we here we don't know that value at t node. This graph might have started with like this, because this value applies from the time t is equal to 0. So the only possible option here which fits is the option D. Let's now move to the next question. An inductor of value resistance is also given, connected in series to a battery of 15 volt EMF in the circuit shown below. The key K1 has kept closed for a long time. So K1 is kept closed for a long time, and kept closed for at t is equal to 0, K1 is opened and K2 is closed. So it means when K1 was closed, so let me write here that case 1, K1 was closed and K2 was open, means our circuit will look like something this. We have inductor here, resistance here, as K1 is K2 is open, so it is out of the circuit, we will not consider it, and this will be our circuit. Means it is a charging circuit. Inductor is getting charged here. Now case 2, when K1 is open, so battery is out of the circuit, or battery, we can ignore the battery, and K2 is closed, so circuit will look like this. Inductor, resistance, and they are connected in series. So here we have discharging happening. So it is basically a discharging circuit. So now at t is equal to 1 millisecond, so time is given 1 millisecond, the current in the circuit will be, so we have to find out that after the case 2, means K1 is open and K2 is closed, after 1 millisecond, what will be the current in the circuit. So as in case of discharging, we know that current in a discharging inductor is given by I node e raised to power minus t by tau, where t will be 1 millisecond, tau is tau will be L by R. So L is 3 into 10 raised to power minus 2, and R is 0.15 kilo ohm. So we can say this will be 0.15 into 10 raised to power 3, or 150. So this will be 50, or 0.02 into 10 raised to power minus 2, or 2 into 10 raised to power minus 4. This will be the value of tau, or the time constant. Now let's figure out value of I node. So I node is the maximum current that can flow in the circuit, and that this current is initially flowing in the case 2 and also flowing in the case 1 when inductor has fully charged. So you know, so value of I node in this scenario will be when inductor is fully charged, then it will act as a, we can say, a simple wire, and then we will have only resistance and battery in the circuit. So I node will be EMF by the resistance. EMF is 15 and resistance is 0.15 kilowatt. So 0.15 into 10 raised to power 3, that will be 15 into 15 into 10 raised to power 1, or 1 by 10 ampere is the value of maximum current that can flow. And now we will substitute this value here. So 1 by 10 e raised to power minus t, t is 1 millisecond, so 1 into 10 raised to power minus 3, and the time constant which we have already solved, that is 2 into 10 raised to power minus 4. So this will become 1 by 10 e raised to power negative zero point -5 into 10. This 10 raised to power 4 will go on top. So it will be basically 1 by 10 e raised to power minus 5, or we can write it like 1 by 10 into e raised to power 5, and e raised to power 5 is given 150. So it will be 10 into 150, or we can say 1 by 15 into 1 by 100. Now 1 by 15 will be, this will be equal to we can say 0.6 0.66 into 10 raised to power minus 2. From here 1 by 50 is 0.66 into 10 raised to power minus 2, or I can write it 6.6 into 10 raised to power minus 3, or 6.6 milliampere. That is option A for us. Let's move to the next question. So first let's slide it slightly. So here we have a LCR circuit is equivalent to a damped pendulum. In a LCR circuit, the capacitance is charged to Q node and then connected to LR, shown as below. If the student plots graph of square of the maximum charge on the capacitor with time for two different values of L1 and L2, means we can change L1 and L2, then which of the plot represents the graph correctly? So we have to represent charge versus time. And we know that this LCR circuit, we can represent it a damped harmonic oscillator. And I think we have already solved this question. Let's suppose that when we connect this capacitor with the resistance and inductor, there is a current flowing in this direction. So this will be positive, this will be negative, positive, negative, and positive and negative for the we can say these devices or inductor or these parts. So now if I write an equation in the direction of the current starting from point A, so if I move to resistance, then positive to negative, I will write negative, and suppose current is I, so it will be negative IR, then negative, positive to negative again negative, and potential drop across inductor is L di by dt, and then again positive to negative for the capacitor, and for capacitor it is potential drop is q by c. So q by c, it should be 0, and then I can write it like I can take negative sign common, so they will become positive, and I can write dq by dt, so it will be L dq square by dt square plus R dq by dt plus 1 by c of q is equal to 0. Now we know for a damped harmonic oscillator we have equation is given by minus kx minus b, and equation for it, this second order differential equation for it, is given by d square x by dt square plus b by m dx by dt plus k by m into x is equal to 0. And solution for this type of equation is given by x is equal to the damping amplitude e raised to power minus bt by 2m. So we take this coefficient and put it in the exponential. So similarly, we can write this equation in this way, that dq second derivative of charge dt square plus r by l dq by dt plus 1 by lc q is equal to 0. And for this, from this one I can write same equation as I write for x in case of damped harmonic oscillator for the charge, and charge will be q is equal to q node e raised to power double of this in the negative. So here it will be minus r t by 2l. Now we have to plot a graph for q square versus t. So we have to form q square here. So squaring both of these sides, we will get q square is equal to q node square e raised to power minus rt by l. And now I can further write it like that, that q square is equal to q node square by e raised to power rt by l. Now let's come back to our original question, that we have to compare this downfall for two different type of inductors. So first of all, if we see here that this downfall should be exponential one. This should not be a straight line. The downfall should be exponential one, because we have an exponential term here. So option A is rejected and option B is rejected. Now coming to the option C and D, that in one L1 is falling faster in L and in the C L2 is falling faster. Now we know that L1 is greater than L2. So if L1 is greater than L2, and if we see this term here, if we have if value of this L is smaller here, then this whole term will be larger as a whole, and then e raised to power that will be higher. So we can say for smaller value of L, q square will be small, and for larger value of L, this q square will be high or higher. Means for smaller value charge is this charge term will be smaller, means it will fall sharply, and for larger value is this value will fall slowly. And we know that L2 is smaller, means L2 term will fall faster, and in graph C we see that L2 is falling faster, means option C is the right answer here. Let's move to the next one. For an LCR circuit shown here, the current observed to lead the applied voltage. Current observed to lead the applied voltage. So if current is leading, means it is a capacitor dominated circuit. So initially it is a capacitor dominated circuit, or in that scenario we can easily say that XC is greater as compared to XL. Now an additional capacitor C, when joined with the capacitor C present in the circuit, makes the power factor to the unity. The capacitor C must be connected in. So we have to find out that where this additional capacitor needs to be connected with our original capacitor C. Either it will be in series or either it will be in the parallel. So as per the statement that power after connecting this capacitor, power factor needs to be unity. Now if power factor is unity, power factor is equal to 1 means cos phi is equal to 1, and for that we know, sorry, this will be 1. So cos phi is r by z, and z is r square plus xc minus xl square. So to make this term unity, we need to make xc is equal to xl. Only then this term will become unity. And as already mentioned that it is a capacitor dominated circuit, means xc is already greater than xl. So as per question, we need to attach a capacitor here. So inductor we cannot change, we can only change this xc term. So we need to reduce this. To make the power factor unity, we need to reduce xc, and xc is given by 1 by omega c. Already omega is fixed, so how we can reduce value of xc? We need to increase the capacitance of the circuit. And how we can increase the capacitance of the circuit? We know that when we connect a capacitor with another capacitor in parallel, then their capacitance adds up. So in short, we need to add the capacitor in parallel with the existing capacitor. So this much we have figured out, that we will add a capacitor in the parallel with the existing capacitor. Only then there is chance that xc become xl and power factor becomes 1. So both series options are rejected for now. Now let's suppose we added a capacitor, that is C dash. So after adding the capacitor, our total capacitance becomes C is the original capacitance plus C dash which we have added in the system. So from that, at this condition, xc becomes xl, or we can say that 1 by omega c plus c dash is equal to omega l, and from this we can write that 1 by c plus c dash is equal to omega square l. Reversing both sides, c plus c dash is equal to 1 by omega square l, and from this c dash is equal to 1 minus omega 1 by omega square l minus c, and I can further write it like 1 minus omega square lc divided by omega square l, and parallel here it is omega square lc by omega square l. So option C will be the right answer here. Let's move to the next one. So in the circuit A and B, switches S1 and S2 are closed at t is equal to 0. And in both in the first circuit we have capacitor and resistance. In the second we have inductor and resistance. both there is a battery, so if we press the switches, both will be in the state of charging. The variation of the current in the two circuits for t is greater than 0 are roughly shown by the figure. So we have to represent variation of the current. Now we know the basic concept here, that at t is equal to 0, at t is equal to 0, inductor act as open circuit, means inductor does not allow current buildup when we press the switch, whereas capacitor act as short circuit. Capacitor act as a wire when we just press the switch. And at t is equal to infinity, reverse happens. Inductor is fully charged, so inductor act as short circuit or a wire, and capacitor act as open circuit. And we also know the graphs for their current, that suppose this axis represents current it and this axis represents time. Then for capacitor curve is for inductor curve is something like this. Current slowly builds up and then reach to the maximum saturation value. This is for inductor. Now for the capacitor, initially current is maximum and then reduces to almost 0. So current follows this pattern. This is for capacitor. And if we compare here, this E by R term is equal to current. E by R is the maximum current in the two circuits in both of the diagrams. So first we have A. In A we have capacitor. So capacitor's current should decrease. Here in the option C, capacitor current is decreasing. And for B we have inductor, so its current should increase. So in option B, here current is increasing uniformly, not uniformly, at exponential rate. So option C here is the right answer. Let's move to the next one. Let's take it some side. In the circuit shown here, the point C is kept connected to point A. So C and A are connected till the current flowing in the circuit through becomes constant. Because it means that A and C are connected until the current becomes constant, means this inductor gets fully charged. Afterwards, suddenly point C is disconnected. So C is disconnected. C is disconnected. And A and B are connected from point and connected to point B. Okay, now C and B are connected. So now C and B are connected. Ratio of voltage across resistance, this resistance, and the inductor at T is equal to L by R will be equal to. So we have to find ratio of voltages across these two. For that we need to calculate the current. And as after charging we have disconnected the battery, so this circuit is in discharging state. And in discharging state, current is given by, in circuit, is equal to I node e raised to power minus t by tau. So let's find out the value of current. So current flowing in the circuit will be I node e raised to power, value of t is L by R, and we know that tau is also L by R. So t and tau are equal here as per the condition. So it will be current flowing in the circuit is I node by E, or I node into e raised to power minus 1, or I node by E. So voltage drop across resistance will be I times R. Value of I is this, so it will be I node times R divided by E. Now coming to the inductor part. Oh, sorry, yes. For the inductor, we know voltage, potential drop or voltage drop across the inductor is given by L di by dt. So we need to calculate di by dt from this equation. So di by dt will be given by I node e raised to power minus t by tau into derivative of this term. So it will be minus 1 by tau, and it will reduce to I node e minus t by tau with negative sign here and tau here. So value of the voltage across the inductor is given by minus L I node e raised to power minus t by tau by tau. This is the journal expression, and we have to find voltage at t is equal to L by R or t is equal to tau. So if we put value of t here, so it will become minus L I node e raised to power minus 1 divided by tau. Again, tau is L by R, so L by R. This L gets cancelled, and voltage across inductor comes out to be minus R I node e raised to power minus 1 or minus IR node divided by E. So we can see that both of the voltages are negative of each other, and that we can simply see from this diagram that there is no battery source, no voltage source is connected. So if plus 5 volt is induced here, if on this inductor we have plus 5, then on the resistance there should be minus 5. Voltage should be in the opposite term, so that total voltage add to 0. Now we can take the ratio. So as they are equal, just sign is opposite. So we can say VR by VL is equal to minus 1. So option C will be the right answer here. So with this, I end this video here. Hopefully whatever I have covered is helpful to you and understandable also. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to resolve them. And if you like this video, then do press the like button, share it, and subscribe to our channel. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.